Hey guys, thanks for coming back with me. So we're going to pick up here with our standardization calculations. We're going to do some more calculations in our concentrations. And so we're picking up here. I had asked you to go away and do this. And so we're going to pick up here. I'm actually going to pause again and do these calculations because I forgot that I was supposed to do them before I came back to you. So I'm going to pause again here and then I'm going to come back and show you the results that I have. Thanks. Okay, so we looked at the standardization of this material a couple of slides ago, and we actually walked through how we get the concentration of the KHP solution. So we take and we do the 5 grams of the KHP, and we divide that by the molecular weight of the KHP, the 204.2 grams per mole. And then we divide that by the volume, the 25 milliliters that they say we dissolve this in, which is right here, the 25 milliliters. And then we convert that to liters by multiplying by 1,000 milliliters per liter. And that gives us a 0.9794 molar KHP. Okay, so that's the answer that I have right here. That's the concentration of the KHP solution. The theoretical molarity of the NaOH is based on the amounts that we put in here. So the 49.326 grams of NaOH in a total volume of 1 liter. So 49.326 grams of NaOH divided by the molecular weight, 39.997 grams of NaOH in 1 liter. Okay, that's equal to 1.2332 molar NaOH. Okay. That's my theoretical. So that's right here. Now my actual molarity is going to be based on the amount of KHP that was used to titrate it. So 49.624 milliliters of KHP were used. Excuse me. Times the concentration of that solution, 0.9794 moles KHP per liter. I do 1 liter is 1,000 milliliters to get the units right. So my milliliters have canceled with the milliliters here. The liters have canceled with the liters there. Okay, so milliliters and liters. And then there's moles of KHP here. I know there's 1 mole of KHP per 1 mole of NaOH. So the moles of KHP will cancel here to here. So I have 1 mole of NaOH, but I need moles per liter. So I divide by the volume that I used in milliliters, 1 over 50 milliliters, because it was a 50 milliliter solution that I was titrating. It said that I had that 50 milliliter solution that I was titrating. Okay. Get to Neptune, where did it say it? Oh, 50 milliliters right there. Sorry. In my office, I just ate lunch and it's nice and warm in here, so I'm falling asleep. So 50 milliliters of solution right there, and then I do the unit conversion, 1,000 milliliters per liter. And then milliliters will cancel there, and that will leave me with an answer in moles per liter. And so if I do that calculation, that gives me 0.9720 molar NaOH. So that's the answer that I reported right here, 0.9720 molar. The percent error is the 1.2320 or 1.2332 molar that I calculated here, minus the 0.9720 molar that I calculated here, absolute value of that, divided by the value that was here, the theoretical, times 100, that gives me 21.18% error. And all of those were what we calculated before. I use the standardized NaOH sample to titrate a 30 milliliter unknown concentration of HNO3. And it takes 37.261 milliliters of that NaOH to reach the endpoint. What is the concentration of the HNO3? The first thing I have to do is write my equation for the reaction between NaOH and HNO3. So I scroll down a little bit and I write that NaOH plus HNO3 gives me H2O plus NaNO3. Okay, so it's a 1-to-1 relationship. I know that I have a 30 milliliter sample of the HNO3 because they tell me that right here, 30 milliliters. And I know that it takes 37.261 milliliters of NaOH, and that concentration of that NaOH was calculated right here. The actual molarity is 0.9720 molar. So that goes down here, 0.9720 molar, and then 37.261 milliliters. And of course, the 30 milliliters for the HNO3 is right here. So I do my calculation, 37.261 milliliters of that NaOH, convert it to liters, so divide by 1,000 milliliters per liter, times the 0.9720 moles of NaOH per liter. So the liters cancel, the milliliters cancel, and I'm left with moles of NaOH. I know that 1 mole of NaOH reacts with 1 mole of HNO3, so that cancels the moles of NaOH, leaves me in moles of HNO3. I want molarity, so I have to divide by the volume in milliliters, so 30 milliliters, and then I have to convert that to liters, so I multiply by 1,000 milliliters per liter, cancels the milliliters, and I'm left with moles per liter. And it gives me 1.207 molar HNO3 as my answer. So I take my standardized solution and I'm reacted against this new unknown acid to figure out, what that concentration of unknown is. Okay. So I go through all the math to figure out what the math is on my standard. It's all this stuff up here. And then I do the same calculation on the titration down here to figure out what the math is for that unknown. Okay. So very similar calculations and concentrations there once we know what that standardized solution looks like. Okay. So questions, comments, problems on our standard, how we do the math for the standard, and then how we apply that to our run. Okay, so that's that. Now, we do have another set of calculations here. Again, I'm going to ask you to do this, and then I'm going to come back and go through this with you. So I'll be back in just a couple of minutes. All right, guys, so we're back. So what we wanted to talk about was, we have example calculations here. Set a 7.500 gram sample of KHP is diluted to a total volume of 1 liter, so 1,000 milliliters. This sample is used to standardize an NaOH solution made by adding 4.120 grams of NaOH, diluting the NaOH to 1,000 milliliters, or 1 liter. The NaOH solution requires 75.42 milliliters of KHP to titrate a 50 milliliter sample of the NaOH. What is the concentration of the KHP? What is the theoretical molarity of the NaOH? What is the actual molarity of the NaOH? And what is the percent error of that? And then I use that sample to titrate a 60 milliliter unknown concentration of HI. It takes 57.624 milliliters of the NaOH to reach the endpoint. What's the concentration of the HI? Okay, so yet again, setting up our equations. I have 7.500 grams of KHP. I divide that by the molecular weight, 204.2 grams of KHP per mole. I then divide by the volume, 1 liter, and that gives me 0.03673 molar KHP, and that is what I reported right here. Calculated it here, reported it here. Theoretical molarity of the NaOH. I take the 4.120 grams divided by the molecular weight of 39.997 grams of NaOH per mole and divided by the 1 liter. That gives me 0.1030 molar NaOH. Okay. I then have a situation where 75.42 milliliters of KHP are used to titrate at 0.03673 molar concentration to titrate a 50 milliliter sample of NaOH. So 75.42 milliliters, 1 liter is 1,000 milliliters, 0.03673 moles per liter, 1 mole of NaOH and is required to react with 1 mole of KHP, and then divide by the volume of the NaOH that was used, 50 milliliters, and then multiply by 1,000 milliliters per liter to cancel all my units except for 1 mole of NaOH and 1 liter on the bottom. That gives me an answer of 0.05540 molar NaOH. Okay, that is what I report right here. My percent error is then this number right here, 0.1030 molar, minus this number right here, the 0.05540 molar, and it's the absolute value of the difference of that, divided by this the theoretical value, the 0.1030, and I multiply by 100. That gives me 46.21% error, since this one is roughly about twice as concentrated, so it's 46%. Now, I use that concentration of solution, the 0.05540 molar NaOH, to titrate a 60 milliliter sample of HI, of unknown concentration. Takes 57.624 milliliters of that NaOH solution to reach the endpoint. So what's the concentration? First thing I do is write the equation. NaOH plus HI gives me NaI plus H2O. Use 60 milliliters of this HI solution, 57.624 milliliters of NaOH, and 0.05540 molar NaOH. 57.624 milliliters, convert liters to milliliters to liters, and then I have 0.05540 moles of NaOH per liter. So that cancels the liters and the milliliters. I'm left with moles of NaOH. I know that 1 mole of NaOH reacts with 1 mole of HI, so that cancels the moles of NaOH and leaves me with moles of HI. I then divide by the volume of the HI that I was given, which is 60 milliliters. Convert that to liters by multiplying by 1,000 milliliters per liter. And that leaves me with a molarity of 0.053 molar HI. I've reported that as 5.3 because this 60 that I got here, no, wait, that actually is 4 sig figs. So 5.05321. Oh. And that is because this should be 60, 0, 0. Oh, not just 60. And that is my fault because I wrote that down. I judge the numbers that I write down based on the number of sig figs that they have. And if I wrote it down as 60 and not 60.00, then I had the wrong number of sig figs. So that should be 4 sig figs, which is then 0.05321 molar HI, which then of course means that that's what I should be reporting here for it. So there we go. So same set of calculations that we've done before. So grams to moles, and then divide by the volume to get molarity, or grams times molarity to get to moles, multiply by the molar ratio, and then divide by the volume to get to molarity. Okay. So this is not a dissimilar process to what we've done in the past. Okay. No questions, comments, problems on our concentrations and how we get to molarity. A couple more examples that are set up here. I'm going to let you go through these and then I will come back with some answers on these. Okay, so since this isn't exact what we were doing before. I decided to do 2 of these without walking through them with you, at least in detail. And I'm gonna do the other 2, walking through them in detail while I do this. So I used 46.328 milliliters of a 0.100 molar standardized NaOH solution to titrate a 50 milliliter sample of HBr. What is the concentration of the HBr solution? Now this is just like what we did at the very end in the last calculation. So I wrote my balanced equation, NaOH plus HBr goes to NaBr plus H2O, and one relationship standard kind of deal. So I have 0.1008 molar NaOH, 46.328 milliliters of it are used. My HBr is a 50 milliliter sample. So I take my 46.328 milliliters of NaOH, I convert that to liters by dividing by 1,000 milliliters. I multiply by the molarity, the 0.1008 moles per liter, and then that gives me an answer in moles of NaOH. That would be moles of NaOH right here. I divide by the moles of NaOH, 1 mole of NaOH from the balanced equation, and then 1 mole of HBr from the balanced equation. Now I'm in moles of HBr because I've canceled the moles of NaOH. I divide by the volume of the NaOH, which is 50 milliliters, or sorry, the volume of the HBr, which is 50 milliliters, and then I convert that to liters. So I multiply by 1,000 milliliters per liter. And it gives me moles per liter on this particular solution. I have not actually done that math yet. Sorry. So, oh yeah, actually I did. Sorry, it's right there. It's 0.09340 mole of HBr. So that's the answer for that particular question. It's right there. So I can see that I actually did do a calculation and an answer. For my next question, I used 78.639 milliliters of a 0.1008 molar standardized NaOH solution to titrate a 35 milliliter sample of H2CO3. What's the concentration of the H2CO3? First, we need a balanced equation. So I have my NaOH reacting with H2CO3, and that actually gives me H2O and Na2CO3. So because this is an Na2, I know that I need to have 2 NaOHs over here. If I have 2 OH groups, I need 2 H groups, which I have, and that then produces 2 H2Os. And so that's my balanced equation. Now I know that my NaOH is 0.100 molar, and I used 78.639 milliliters of it. And this sample is 35 milliliters. So I brought that calculation down here. I said 78.639 milliliters, converted to liters, divide by 1,000. And then I multiply that by the molarity of that NaOH solution. So 0.1008 moles of NaOH per liter. And that leaves me with moles of NaOH. I then divide by the number of moles of NaOH. 2 moles of NaOH are in the balanced equation for each mole of H2CO3. So I divide by 2 and I multiply by 1 mole of H2CO3. And that cancels my moles of NaOH. So I only have moles of H2CO3. I need to get to molarity, so I need to divide by the volume. So I divide by the 35 milliliter sample that I had, and then convert that from milliliters to liters by multiplying by 1,000, because there's 1,000 milliliters in 1 liter. And that leaves me with this answer, 0.1132 molar, and that's H2CO3. And remember, we talked about, we need to take this mole ratio into consideration when we do this. So if this had been, one of these situations where I wasn't taking that into consideration, I would not have gotten this right. This would have come out to be the wrong number and would have been twice as high as it should have been because I did not take this ratio into account. I'm sorry. Hold on. Let me get that back. I apologize. but it would have been twice as high because I didn't take this ratio into account. So not taking this ratio into account would have meant that this would have been 0.22 something, and that would not have been correct because of the ratio that it should have been. Okay, so I'm not sure exactly what's going on here. So I'm gonna go ahead and stop here for just a moment and get us a new recording, close a couple of things out to see if I can stop it from glitching out on me like this. Okay, all right, talk to you soon.